everyone, and welcome back to another Math Research Live with me, Charlotte Aten. Oh yeah, I guess there were 180 seconds left, and now there are maybe negative a few seconds left. So yeah, it's great to be here. It's lucky number 13, I think, of these things that I've done. This is the 13th one, so that's pretty exciting. So I was hoping from last time that I would have a new preprint posted that was actually mostly stuff I had done when I was in grad school, but it ended up taking longer than I thought to get it prepared, so it's still not quite there yet. I decided I wanted to update a bunch of things and, you know, trying not to let the perfectionism get the best of me, but I just didn't quite make it. So I'm still going to talk about what I've been thinking about, because I also figure that, you know, I'm posting this online anyway, and probably no one will try to scoop me on these things. And you know, as always, I'll just be happy if people are curious enough to check them out with me. So yeah, hopefully though, this week, fingers crossed, I will actually post something new. Oh yeah, actually each of these is 3 hours long, so that means that I've done this. If you want to do a marathon of this, I've done 36 hours so far, and this is going to take us up close to 40. I'm only going to go for 3 hours today too, probably, but yeah, yep. This year I've streamed almost, you know, I've streamed 36 hours. It's a day and a half at this point straight. If you just watch the whole thing, you can do part of your day, fall asleep, wake up, and I'll still be talking about math. Alright, well, anyway, oh, no, this is the one I want. Thanks for being here with me, as always. Yeah, so, I'm sure I have more than enough. When did I start streaming this year? That's a good question. Maybe April? Do you remember, Nova?
I want to say it was in May.
May?
Not sure.
Possibly May.
It was early summer.
Yeah, it was early summer, and I took a few weeks off because I got COVID. I actually, yeah, if you want me to take a look at something and it's close enough to my interest that I would be able to say some interesting things about it, that would be really cool. Yeah, I think that would be a really cool way to engage with people. I feel like I haven't done as much of that as maybe I ought to if I'm interested in growing this. Nova was just pointing out to me that I really should get on, like, maybe TikTok or something with more people. I do actually have a list of things that I might make TikToks about. I just haven't done it yet, you know. So I'm trying to settle into my new postdoc job at the moment, but I'm definitely thinking I might want to try to put some more energy into growing this as well. So yeah, if you have something you'd like to request, you can either email me, or you can send me a message on Mastodon, or you can even post it in the chat. I can't promise, you know, that I'll do whatever it is, but I will take a look and I can let you know. So no pressure though. You don't have to post it right now, for instance, if you don't have it. Hello. Welcome to the stream. Okay. Oh well, I guess, okay. You're okay with me looking at it right now, so let's see if I can. Oh, hey, that's a nice suggestion, actually. Yeah, huh. Well, I mean, so I guess are you aware of the relevance of this one to me, or is this just a coincidence? So yeah, yeah, and it's yeah. So actually, so it's interesting. Well, okay, what do I want to say about this? Yeah, so I'd be happy to talk. Okay, so I'd be happy to talk about polyhedral products. Here, let me actually copy this and put it into like a text file or something. Or actually, maybe can I just paste the text in here? What happens if I paste the text in here? All right. no, that's not what I wanted. That's not helpful. You know what? I'll just write down the archive. I'll just write down the archive number. All right. So or well, no. Why don't I show you all in my browser? Why don't I do that? All right. That's what I'm going to do. Come on, browser. Okay. Okay, that's, all right, I guess I have to copy and paste. Who's your professor? Is it one of the authors, or, I mean, you don't have to tell me, obviously, you know, if you would prefer not to. Okay, there we go. Okay, so this is the preprint in question. So it's about polyhedral products, and so the relevance that this has to me is that when I was in grad school, well, even when I was an undergrad, so I was an undergrad and then I was a grad student at the University of Rochester, where Fred Cohen was for many years, and so I believe this is actually Ralph Cohen, if I remember correctly. So there's two different Cohens. So Fred Cohen. Oh, okay, cool. Yeah. So yeah, he's one of the authors. So Fred Cohen at Rochester taught my undergrad and topology and graduate topology courses, and so definitely was a big fan. I had a lot of fun in his classes, and I talked to him outside of them. And I remember that maybe when I talk about this, I can even talk about how. So he had. It wasn't like a huge, it wasn't like a huge thing. It wasn't like something that took forever. But he had a fun problem that as far as I know, was like truly like hadn't been answered or something. So Fred Cohen passed away a couple years ago now, I guess. Time goes by pretty fast, huh? Well, anyway, so he had this problem that he had given about polyhedral products, and I remember I'll show you the calculation that I did. I don't think I ever posted it anywhere, but he wanted to know like what the genus of some family of polyhedral products was, and I was like, can't you just, like compute the Euler characteristic and that'll give it to you? And so I did that, and he just basically said that, like, to his knowledge, I think no one had done that. And it wasn't, like I said, it wasn't like the longest thing in the world. It's not like a paper that I posted anywhere, but it was a cool thing, and I had fun doing it. So I'd be happy to talk about polyhedral products. I do not know if Fred Cohen is related to this other Cohen. There are many Cohens, and they're not all directly related to each other, to my knowledge. It's a somewhat common last name. So, and it might be the same. It might be the same origin as Cohn too. I'm not entirely sure. But yeah, there's a lot. There's a lot. So, but yeah. So I can maybe share some stories about Fred too, and that might be cool. Yeah, so thanks for the suggestion. I'll definitely make sure to bookmark this and remember that it's a thing. Yeah, that would be really cool. Thanks for the suggestion. I forgot about that puzzle that I solved too. That's good. That at least I'll have written it down somewhere or posted it somewhere online. Although I'm sure maybe other people have already done that and posted it since then. But yeah. Yeah, it's a small world. So the reason why 13. So this is lucky. This is lucky number. This is stream lucky number 13. And the reason for that is that if you write out the list of all the numbers, and I'm not going to write them all because it would take too long, but you can imagine. And then you start, you get rid of like every second number. Then you end up with like 1, 3, 5, 7, 9, 11, 13. and then you get rid of every third number in this list. No, is that right? Let's see. I feel like let me see. 1, 3, 5, 7, 9, 11, 13. Every second number, and then every third number. Oh, it's because I miscounted. That was the problem. So you get rid of every third number. So here's 5, and then 1, 2, 3. We get rid of 11, and then 13 would survive. So then we'd have 1, 3, 7, 9, 13, and then, well, let's see. We'd have 15 would also survive, and then not 17, but then 19, and so. Yeah, I don't know. I've never been to ICM, so I don't know if everyone knows each other. I do know that the joint meetings is definitely way too big, and not everyone knows each other there for sure. Like, there's too many people. Maybe the plenary speakers pretty much everyone knows, but even that I can't guarantee. But yeah. Okay, and then you do every fourth number, and so on and so forth. So then whatever's after 19, and so yeah. I know what it is. I've never been. Yeah. Yeah. So then if you keep doing this process, then you do every fifth one in the new list. And eventually, like, this segment will be the things that survive forever, because then you take things away that are further down in the list. And so the numbers that show up here, these are the lucky numbers. Yeah, I actually am not. I've heard of DEF CON, but I'm not super familiar, because I'm not that much on the applied side, I suppose. Not enough to have gone to such conferences. And so ICM is definitely like the big international math conference, to my understanding. So I don't know if it may be bigger than the joint meetings. I'm not sure. The joint meetings definitely always has a really large number of people, like maybe 5,000 or 6,000. But it's definitely, I think, much more primarily like North America. It's the big American one. Oh yeah. So anyway, 13 is a lucky number. So that's why I was saying it's lucky number 13, because it survives this, whatever sieve this is. Alright. So let's see. What's the population of people on chat like today? Did people see what I did last time? I should remind everyone of what it was that I was talking about last time. At least that's the charitable thing to do, right? Not to just say you should go watch this 3-hour-long stream from last week. Okay, so well, what I was talking about was this area that is topological lattices, and so these are like topological groups, but instead of ICM is 4,000 people now, or JMM. So if you have some lattice, and well, I'll give you the actual formal definition. So if you have some lattice and then some topology tau, so what is a topological lattice? It's a thing like this. Where this is a lattice. Oh, there's 4,000 people in the chat right now. Yeah, I'm a bit skeptical of that, actually, but okay. It's definitely possible. I would believe 4. 4, I would believe. I'm not going to check, but I think 4 is much more realistic than 4,000. I truly cannot believe that 4,000 people would show up to this right now. What do you disagree, Nova? Do you think that there's 4,000 people watching me define a topological lattice?
Based on the trends, I'd say it's unlikely.
Yeah.
I think we're averaging 10, maybe 9.
I think that's like 9 or 10. No, it's more like 20 throughout the whole course of the stream, but like for like consistent people. At any given time, it's 9 or 10?
Usually.
Really? Do you actually keep up on the numbers for my streams? Oh, really?
I don't watch every stream, but the streams that I've seen, it's usually 9 to 10 at any given time.
Oh, you mean like the ones that you're actually in live? Or do you watch them after I post them on YouTube?
I usually just watch them live.
Oh, okay.
So, I don't know what the views are on YouTube. They're probably a lot higher.
I see. Okay, well, in any case, just as always, just let me know if you don't know what I'm assuming. But yeah, I think that saying let this thing be a lattice will be something that people might not know. But I'm just gonna keep going until there's a question, I guess. So. Or does everyone here? I guess if you chose to be here and listen to me, there's a chance that you know what I mean by a lattice being a set with a meet and a join operation. So anyway, this is a topological space. So tau is the topology on L, and then the last thing is that the meet and join are continuous with respect to the topology tau. So that's what a topological lattice is. And I talked about some examples of these last time, and I had a question which wasn't totally answered, but I started making progress towards, related to the nerve construction. But I'll just remind you of the example that I talked about last time, and show you one thing that I realized that I was working on like retyping up a paper that I had written when I was in grad school, which hopefully I'll actually post the new version of on the archive soon. And when I was doing that, I realized that I had actually managed to give what I felt like was a better description of the operations on these topological lattices. I called these things bottom and top last time, but I'm going to call them 0 and 1L now, I guess. I changed my mind about that. So the idea was that you had this thing, and you were going to somehow make this into a topological lattice where this is like the square. So like this is actually like what, the square, like the 2D thing that you would normally think of. And so that's the idea, is that we're going to somehow make a continuous version of this. And so as was discussed last time as well, the way to do this was actually using that nerve kind of construction, where you don't really have to know what that is, but basically we're going to take each chain, so each like increasing sequence of things, like maybe 0 is less than A is less than 1, so every chain like that, and we're going to turn that into a corresponding triangle that's like the triangle that belongs to that chain, where we think of the vertices as being like 0, A, 1. Just pretend that says 1. So so that was the idea. And now there was actually a way to accomplish this that is described in a number of the papers on this type of thing, which is that what you can do is you can consider all of those functions from your elements of your lattice to the closed interval between 0 and 1, with the property that if I look at these sets, these like kind of level sets, Fs, where by definition this is all of the things in my lattice where f of x is greater than or equal to s. If I look at all these, the condition is that I only consider functions f with fs a principal ideal for each s. Okay. So that's like the definition that is given many places, and so that would be what I guess is so gamma of L would be the set of all functions f like this with the property that's with that property that property. And so it turns out that gamma of L is actually like the geometric realization of the order complex for this lattice. So like this construction does actually do what it's supposed to do. So I'm not going to go through showing that, but the thing about this construction is that you can put the structure of a topological lattice on it, and then the way that's done is by saying, so then this thing inherits a lattice order from the partial order where f is less than or equal to g when, point-wise f is less than or equal to g. So if you restrict that ordering to such functions, then this actually gives this order complex, this geometric realization. It gives it the structure of a lattice. Now the thing is, that's not very helpful to us really in computing things necessarily, because it feels like to me it feels like it's not really quite as natural, I guess. Like it feels like it just, I don't know, it just kind of feels like not as direct. Like I'd like to really be able to define the meets and joins in terms of the meets and joins for the original lattice somehow. And so that's what I had figured out to do it for a specific class of these things that I was interested in when I was in grad school, and then I realized that description I could actually make to be general. And so I guess unless there are any questions or anyone wants to see like more detail about like the original setup, I'm going to describe what I've been thinking about this, and hopefully finish typing it up at some point in the not too distant future, so you don't just have a video. All right, is there anything that anyone else is thinking about, or any of the 4,000 people in the chat right now? Yeah. This would be like the most polite group of 4,000 people in the world. It's like everyone's just very shy. Okay. Let's see. Okay. So what was I thinking? Well, if you remember, what we can't do is we can't just take you know, we can't just define the operation on convex combinations of the original elements. So if you remember, maybe I'll just illustrate quickly again. If you'll recall, for instance, if I do something like you know, I don't know, if I say like I take one half A plus 1/2 times this 1L, and I do the meat of it with itself, I should just get itself, right? But if I just assume that this is bilinear, and then I just try to extend, like in like the obvious way of making the meat like distribute over the addition. Oh, things are being activated here. Let's just. So if I just assume that this works like the obvious way. Oh, here I'm doing my air quotes. The obvious way. There's the air quotes. Then I would come up with something like 1/2 times 1/2 times A meet A plus 1/2 times 1/2 A meet 1 plus 1/2 times 1/2, and then 1 meet A, and then 1/2 times 1/2 times 1 meet 1. And then when I do this, I would see that, well, all of these things are A's, and then this is 1, and so I'd end up actually getting 3/4 A plus 1/4 1, and this can't happen. This isn't allowed, because the meat of anything with itself is supposed to be itself, and so this violates the axioms for a lattice. So this is not the correct way to do it. But we would like something that's like this, where it's somehow defined like coordinate-wise based on the original lattice. And so I had given a special case of this in the thing that I wrote up when I was in grad school, that I'm hopefully going to post some version of hopefully this week now. I'm gonna show you what I've been thinking, and I think that this just actually works. I think that this just actually works in general, and I just didn't get time to type it up. Okay. So what do I want to do? What do I want to do instead? Well, if you remember last time. I had said, well, you know, we can think of, if we have a function from our lattice to the interval from 0 to 1, if we want to, you know, there's really only a finite amount of information here, right? If our lattice is finite, I'm just going to assume that L is finite. You can probably honestly do similar things to what I'm about to do with infinite ones, but I just haven't really thought about it yet. It's the usual thing where there's going to be convergence of issues to, you know, consider, at least. Well, if it happens that our lattice is the one I was talking about before, where this set has 0, A, B, and 1, then what I can do is instead of thinking of f as like a function of this, I'll think of f as being this, you know, this tuple. You know, I'll use notation and think of the tuple, which is what 0 gets sent to, what A gets sent to, what B gets sent to, and then what 1 gets sent to. And so if I do that, so my goal is to somehow have a definition of how meets and joins work that is compatible with the idea of taking convex combinations of the original elements of the lattice. So in other words, I want something that's analogous to this, but where I actually define how to do this on the components correctly so that I get the correct formula. and that should agree with the formula that would be like that should agree with this definition of inheriting the partial order from the ordering on the functions. And so I guess what bothers me, which I haven't thought too much about, but I guess what bothers me is that well, okay, I guess there's two things. This description, it tells me that I need to choose functions that have this property, but that's not really like giving me a construction in the sense that it's just telling me to choose a function that has that property. And so I can like actually grind through that in whatever examples and start to get some intuition for what it's saying, but it definitely feels less natural than taking a complex combination. And so it feels like less of a recipe for how to construct the functions that are on there. And then a secondary concern, which I actually haven't thought about, or at least not in so long that I don't remember, is are the meets and joins really just what, like, you know, what you might guess, like of taking like the you know, just taking like the pointwise like the mins and the maxes. I'm not sure about that, and I kind of don't want to think about that. It seems unpleasant, especially to do something pointwise on, you know, I mean, it's just, I don't know, it bothers me for some reason. Like, I just feel like it's less natural, you know. Okay, I guess it's only a finite amount of points, really, if the lattice is finite. So I guess that's what it is. But I feel like, I have a concern. I haven't thought about that example, but I want something that's in terms of the convex combinations. I feel like that will be the most natural, and it will also make it perhaps the most obvious that this is actually the geometric realization of the order complex. Like, I feel like that'll be more obvious to me. So anyway, I want a different way of doing this, and you know, so it's not like that was wrong or anything, but like I want a different way of doing this that seems more intuitive to me. And so I have these vectors, and well, I want to be able to represent this in a way that is in terms of the convex combinations of these original elements. And so what I'm going to do is, I know that the special functions that I might want to consider are these, what I might call phi sub x, which are the indicator functions of the elements in the lattice. So this phi sub x of phi sub x of y, I guess. I'm going to take this to be 1 when x is greater than or equal to y, and it's going to be 0 otherwise. And so, in other words, this is the indicator of the principal ideal or the principal downset of all of the things that are you know, for each individual x in our lattice, we have such an indicator function. And so this thing I'm going to think of as being identified with the element x from the lattice, the original discrete lattice. And so, well, one thing to note is that these things actually do satisfy that condition that I mentioned before. So if I take this indicator function and I look at the S level set, right, by definition, this is all of the, I guess, y in the lattice with the property that f of y is greater than or equal. Oh, sorry, not f. That phi x of y is greater than or equal to s. And so, well, there's only two possible cases, right? Because, you know, if s is equal to if s is equal to 0, then well, what is that going to mean? That's just going to mean that phi x sub s is just everything, right? Because it's just going to be the whole lattice, and that is actually the principal downset. That is actually the principal ideal generated by the top element. It's 1L, so that's fine. So that we're good with that. If S is greater than 0, well, that means that the only stuff that's going to satisfy this condition is the stuff that makes phi x of y 1, and so that's just going to be all of the y's that are less than or equal to x. So then, because of this, in this case, this is just going to be I meant for a square bracket here, the principal ideal in the lattice. So this is just going to be x, the principal ideal generated by x, all the stuff that is below x, including x. So, all right, are people cool with this so far? Okay. Well, just let me know if you have any questions or comments. Okay, so these things are definitely points, and so now what I would like to do is I would like to consider convex combinations of these things, and so I'm actually gonna write down the example that I had thought about before. That was like how I was thinking about this. So let's suppose that I did a convex combination of these that was like 1/6 phi a plus 2/6 phi 1L, 3/6 phi 0L. Okay, so that's definitely some convex combination of these guys. And okay, well, I guess actually before I talk about what that would be, before I talk about what that would be, maybe I'll come back over here and I'll point out that, so if I do phi 0 in our other notation, that's the same thing as saying that, okay, everything that's less than or equal to 0 gets sent to 1, so that's just going to be 1 and then all zeros. And then if I do A, so I went 0, A, B, 1, so everything less than or equal to A. And then phi B would be like this. And then phi 1 would be like this, just everything. And so, well, maybe I'll make a new page. So then, if I take this, for instance, this is a convex combination of these things, and if I actually write out what that would be, it's 1/6, and then this would be 1, 1, 0, 0. Well, 1/3, and 1, 1, 1, 1, and 1/2, 1, 0, 0, 0. And so at the end of the day, I'd still get a 1 here, and then I'd have a 1/6 and a 1/3, so 2, okay, so that's 1/2. And then in the next spot over here, I'd have just a 1/3, and then in the last spot, I would have also a 1/3. All right, and so this is like the information of just some typical function f that should satisfy that condition. So like we could check directly for this one that it satisfies the condition that makes such a function or such a tuple actually be you know, that this is actually in gamma of L. You know, I guess in general, you would want to, you would want to verify that taking convex combinations actually still satisfies the condition. But maybe let's just leave that for now. So the question though is, if I want to take meets and joins of things that are like this, how do I do that directly in terms of these components? Or in other words, how do I translate between this presentation and this presentation? That would be a helpful thing to be able to do. And so what I ended up thinking was that, well, if I wanted to go from this presentation to this presentation or vice versa, so what I want is, I basically want to compute that, I want f to actually be, so maybe the sum of, over all the elements of the lattice, I want it to be some, I want there to be some coefficients, maybe ux, then these phi of x's, where the sum of all of the u of x's is equal to 1, u of x is between 0 and 1. In other words, I want to write f as any f that satisfies this as a convex combination. So how do I find what these coefficients are supposed to be? Is the question. So, well, of course, in any specific case, right, you could maybe set up a system and solve, but you want to have a systematic way of doing it from knowing that you're given an f that satisfies the condition. You want to know how to compute what this is. And so so then what I was thinking was, well, there's a quantity, I don't know, maybe I'll call it f tilde. There's a quantity that I could associate to a given element of the lattice, which is, I could look at, so what I was thinking was, the reasonable thing to look at is, I should look at the supremum of all of the choices of S in this interval, where this f sub S is actually the principal ideal determined by X. So like for this particular choice of f, so if f is 1, 1/2, 1/3, 1/3, then, well, this f tilde, so f tilde of the 0 element, well, what's the biggest S that I could choose, so that I get that f sub S is just the set that just has 0 in it, right? So in other words, what is the biggest value of S that I can choose, where if I look at all of the things that are, just to remind you, so what's the biggest value of S I can choose, so that when I look at all of the things for which, here, let me find my original definition. So if I look at all the things for which f of x is greater than or equal to that, I'm just going to get just the 0 element of the lattice. So what's the biggest S I can choose that will make that happen? And that's actually 1, right? Because if I just choose S to be 1, then I'll just get, well, this is the only thing that has 1. Okay, so that's 1, and then by similar reasoning, this f tilde of A. So what's the biggest thing I can choose for my S, so that if I look at all the things that get assigned a value that's that's at least S, then I get 0 and A. So that would be 1/2. Because if I choose a value that's any bigger than 1/2, I'll only get 0. I'll only get the 0 element. So by similar reasoning, 1/2 is the biggest thing I can choose to just get A. And then I'll skip B for a second, and I'll say, okay, if I want to get the principal downset determined by 1, in other words, everything, what's the biggest value of S I can choose so that all of the things that get assigned a value greater than that is everything? Well, that would be 1/3. Okay. So, yeah. So I have that, and so then finally, for B though, so then this is where this supermum really comes in. What is the largest value that I could choose from the interval from 0 to 1, where choosing that value for S would give me the principal ideal for B that's generated by B. And the answer is that, well, there isn't one, but if I think about the supermum as being the join of all of the elements of the interval 0 to 1 that satisfy this, then the empty join should be 0. So it should be the bottom thing. So by an appropriately technical reading of what the supermum means, the F tilde of B should be 0. Okay. So that's okay. So that's something. But then the question is, how do we use this information to recover the original, to recover the convex combination, right? How is that supposed to give us the convex combination? So I was actually kind of proud of myself, because I remember like looking over a little bit whatever I had written up years ago about like this coordinates for this specific case without having all of this in it. And then I remember messing around a little bit and then thinking to myself, I'm pretty sure it's this quantity that's like the important thing to mess around with. And so I think that this actually does work out. And so okay. And so the idea then was that what I would like to do is I would like to define, well, I don't want to say this. So I have these quantities, but then I have to somehow use these quantities to get back to the actual coefficients for my convex combination. In other words, somehow I should get 1/6 for A, 2/6 for L, and 2/6 for 1, and 3/6 for 0. So how do I actually get those? Okay, well, so somehow I want, maybe I'll just copy that. That would make my life easier. Okay, so somehow I want this. And so the idea is then that, well, 1/6, well, 1/6 is equal to, it happens to be equal to 3/6 minus 3/6 minus 2/6, which is 1/2 minus 1/3, which is this. And then similarly, if I were to do, say, 2/6, then, well, let's see, for 2/6, well, okay, that is exactly 1/3, which has the virtue of being f tilde of this one L, the top thing. And then for 3/6, well, for 3/6, that's supposed to be the coefficient of 0, and so, well, it's 1/2, but this also can be written as how do I want to say this? So the coefficient of 0 is 3/6. So here I had a, and then I subtracted off the thing that was bigger than it. Here I had 1, and there was nothing bigger than it. But here I end up having 3/6, and okay, and then yeah. So then I was thinking that what I wanted was that. Oh, so I usually say 3 areas. Which you can also see if you go to my website. So I usually say universal algebra, combinatorics, and category theory. And so actually this has a pretty good overlap of all of the things that I like. So this has some combinatorial stuff to it because of maybe order complexes, counting things, right? So this thing that I'm messing around with right now is adjacent to like topological combinatorics or geometric combinatorics, but there's also some like category theory things looking around. Lattices are particularly nice categories. I was talking about the nerve last time, so there's some of that going on, and then I also like universal algebra, which is why I'm talking about lattices and not maybe just like posets in general, because those are an interesting algebraic structure that's not groups or things that are basically also monoids and semi-groups and things are in the family of things that are like groups, and so lattices are one of the other main types of algebraic structures that come up a lot in universal algebra and logic. So so that's a pretty long answer, but it's my live stream, so I can rant about what I do, I guess, if I want to. So I'm in the foundations group in the department at CU Boulder. So foundations is, generally it makes people assume that I do set theory or that I do logic, and I think logic is more true than set theory. But I mean it's where universal algebra goes because it's the equational logic and the adjacency to model theory and stuff makes it like too foundational for the pure algebra group who's doing algebraic number theory or just finite groups or representation theory or something. I don't know. I do like representation theory, and part of my thesis was on it, or on like representation stability, but yeah, I'm not actively working in that area. So I hope that this was a long, winding answer that gave you some kind of information about what it is that I do. Would you like me to clarify anything or make anything less clear, maybe? Because I can probably do both of those. I'm not sure if I can do them both at the same time, but I can try. Okay. Yeah. So I guess I'll say too that so I guess that like my philosophy, I suppose, is that I would like to try to have some aspect of the classical mathematician who maybe I can't hope to be a polymath who contributes to 8 different areas of science and speaks 12 languages and is also like a well-respected poet and all of these other things. Oh, I can do that. I can do.
You've
all
already
of
done
that.
half of that.
I have not done half of that.
How many languages do you speak?
I speak I'd say maybe 3/4 of a language.
And you're a third to a fourth of the way through your life.
So at the end, I could maybe speak one language fluently, possibly. See, I don't really speak English. I just make noises that people generally perceive as English, but I actually don't understand language at all. I'm just extremely lucky. Like, if it was a video game, my luck stat is completely maxed out. And so I just kind of do whatever, and people respond as though it's an intelligent piece of information.
How many areas of applied math have you contributed to?
Well, I actually don't have anything applied published, but I do have one paper accepted, and I have a couple other ones that are in preparation. And so it would only be 2 different areas of applied. Nova asked how many areas of applied math I have contributed to. So I have the machine learning stuff. And then I also have some stuff that's related to formal verification or to concurrency, but I don't have that posted yet. So it hasn't been submitted.
So you've done 2 out of 8.
2 out of 8 areas of applied math that I'll contribute to.
And then you do the languages for sure. You love linguistics.
Okay, but I can't actually. I'm not really fluent in another language.
Yeah.
I can only have very primitive conversations.
Okay. And then you also have made fractal art. So that's the art thing that you do on the side.
Yeah, but the fractal. Okay, Nova's telling me that I'm also an artist because of the fractal art. But yeah, no, I mean, I can hold some kind of conversation in French and Spanish, and I know small amounts of. Oh, I've actually been able to have a conversation in Chinese and Arabic before, but I'm not very good anymore because I'm out of practice. I also know small amounts of Malaysian and Korean. I can actually read Hangul. I can read some Chinese characters. Like, I have been able to write paragraphs in Mandarin Chinese before, but I don't remember enough now. I only know a few things. I'm trying to remember what else. Anyway, the point is I only speak about 3/4 of a language. Huh?
Don't forget about Polish.
Oh yeah, I know a few things in Polish too. No, so here's the sad thing. So so I'm thinking about actually taking a Spanish course for professors at CU Boulder, which starts later this semester, so I might still have a chance to do it this semester, because I do want to get more practice. But the problem I found is really that, I was in a very cosmopolitan environment when I was in grad school, because the University of Rochester has lots of Chinese people. There were lots of South American people, Central American people. So I had the good opportunities. There was a lot of people who spoke French, but the problem is that people will occasionally entertain you, and it's amusing to them for you to try to speak their language, especially when you're in America, which I am most of the time still here. People want to practice their English more. People need to use their English more than you need to practice your other language, and they are already able to function in America speaking English, which means their English is much better than my Spanish or my Chinese. And so then it's even though it's kind of polite in some sense for me to try to speak the other person's language, it's a little bit torturous, because unless it's a really casual social setting, they don't want to have to struggle with me just barely being able to discuss the weather. So every once in a while it might happen, but for the most part, if we need to talk about math or getting something done with running a course or whatever, nobody wants to take the time because it's annoying, I don't want to burden people with me struggling to make myself understood when they already speak English so well. And so it happens kind of on a global scale this way, because everyone's English is going to be better than my version of their language, and I don't want to, I realize that asking them to speak English is a kind of imposition, but I feel like it's a less awkward imposition than being I'm going to struggle to speak your language even though I could readily communicate with you in English. So I'll do as much as I can, but it's I don't know. It's something I'm trying to get better at with Spanish, because there are so many people who speak Spanish here. So occasionally I will try to have some amount of casual conversation at work in Spanish, but it's usually quite limited, So yeah, I mean, that's kind of the state of things. But I'm really hoping that, I don't know how long I'll be in Colorado, but I'm really hoping that while I am, I actually improve in my Spanish. Yeah, so I mean, there probably are. I mean, I can just try to speak to Spanish-speaking people in the department as well. But yeah, as I mentioned, it's kind of, you know. But there are courses that the university runs for professors for languages, and so I'm thinking that I might start doing those, even though it's another thing for me to do. You know, but I think it's important to me, and I know if I keep putting it off, that I'll be 40 or 50 years old and I won't have done it. So I want to progress beyond just being able to like mostly read Wikipedia in Spanish or whatever. I'd like to actually be able to have like, you know, at least a regular conversation, if not be able to talk about something more sophisticated, you know. But yeah, I mean that's kind of the situation. So yeah, I hope that I can do that. It's just, yeah, it's yeah, that's kind of where it's at. But also, I guess the other thing too, one other language thing is that I'm thinking that so there's a lot of stuff there's a lot of universal algebra stuff that is in Russian that's from the Soviet Union that sometimes I can't even get copies of it, but sometimes I can, but I can't get optical character recognition to work on them very well, and so I can't easily use machine translation to read them. And so one possibility is that I could learn Cyrillic well enough to just type the Cyrillic letters into the computer and then have a machine try to translate it. But I'm thinking I might just actually try to learn enough Russian that I can read math in Russian. Since I can already I can do it serviceably in French, I might as well, you know, finally learn enough Russian to do it in Russian too. But yeah, that's kind of where I'm at the moment. Yeah, I definitely will think about. I'll definitely think about finding a language exchange online. But yeah, if it could be something that's in person too, that has like a regular schedule, that would also be good for me. Yeah, I should look into it more, because it's at the point where like I can have some kind of conversation, you know, like, and especially if I'm allowed to look stuff up. If it's like emailing or something or texting, like I can do that to some extent, you know, like I can do that to some extent. But yeah, I really should actually try to work on it more, because I keep thinking like, oh, I'll read books, and like I do grammar exercises, like grammar books sometimes, or like tapes, but like, yeah, without having like a reason to use it all the time, I'll like never get like fluent, you know, and it's frustrating. So okay, so I should look up Math Wizard on eBay. If you're, so if you're, let's see, you're just recommending where I could get Russian math stuff in general? Because like, I mean, I'm not sure, but like my problem is like sometimes Western libraries do have copies of books that I'm interested in, but I see. Okay, thank you for the suggestion. I'll check it out. But there's also a lot of papers that, like, my understanding is that what happened was that the Soviet Union had these like local journals that they set up for universities in different regions in the Soviet Union, and they really encouraged or pressured people to publish in these local journals, even though they weren't like these big international journals that everyone was reading, with the idea that they would become like more well known and achieve a wider circulation as the Soviet Union became like more wealthy and more influential or whatever, right? But what actually ended up happening was that the Soviet Union collapsed, and then these things were primarily stored as paper in these libraries in different parts of what was the Soviet Union, and there's not enough incentive for people to digitize all of them. And so, what do you have, buddy?
Oh, it's a piece of his first toy. Where did that come from?
Really?
Yeah.
Wait, what was it? What toy was it?
It was a long squeaky.
He had a long squeaky, and he has where did this come from?
I don't know. I've been going through old stuff to get my stuff organized. I must have loosened up something.
Buddy, I don't know if this is safe for you anymore. It's too small. You might swallow it, bud.
He was
Oh,
so
Dobby.
little.
Oh, buddy. I know. Maybe we'll
sorry,
keep this as a
Dobby.
keepsake, bud, but you can't play with it anymore. I know. I'm
You're sweet,
I'm
baby.
sorry. Oh, you can't see because he's off camera a little bit, but he's being very sweet. Oh, okay, Dobby. I know. I can't give it back to you though. I'm sorry. I'm very sorry, buddy.
He's so sweet.
Oh, Dobby.
Do you want to play with your cactus?
Oh, he'll play with his cactus though. He has a different toy. He found a piece of his old toy from when he was younger, and yeah. Okay, he's fine. He doesn't even remember now. Yeah, rip toy. It's been so long I don't even remember it. All I have left is whatever this is, apparently. This piece, it was a long green tube or something. Oh. Yeah, but so the Soviet Union did not end up becoming more culturally dominant, and then these things are like referenced in Western journals, and like people at some point had access to them or had copies of them, but like it's really hard to find a lot of this stuff now, and like yeah. So I mean, but the stuff that I can find, I would like to be able to read enough to translate some amount of it, because you know, I think I finally started to accept that I just need to learn some Russian. Maybe not to be conversational, but at least, yeah. I think my goal for being conversational really is Spanish, because that's really what I'm around the most right now. Yeah. I mean, that's kind of where I'm at the moment. But yeah, thanks for all the awesome suggestions. You know, I definitely should find people to practice with, and it would definitely help to have more Russian textbooks and stuff to practice reading math with too. Yeah, so that's the language situation. Oh yeah, so as far as, I guess I'll maybe get back to this, as far as this goes, so here I had f tilde of a minus f tilde of 1. Here I just had f tilde of 1, and now for 0, well, it looks like my coefficient should be 1/2. And so, okay, so I guess here's the thing, maybe, is that, well, it does happen that f tilde of a is 1/2. It kind of looks like what's happening here is like, so 1 is above a, it's the only thing that's above a, and I'm subtracting that off. And then 1 doesn't have anything above itself. And so it's kind of looking like this is f tilde of 0. And then so this f tilde of 0 minus all the stuff that's above 0. So if I do this, for instance, no, it's not all the stuff that's above 0. I feel like I convinced myself that this made sense before for some reason. So let's see. Why was I thinking this? So 0 gets sent to 1, and then if I subtract 1/2, I will get to Now I'm thinking that maybe this wasn't what I meant, or am I misremembering what I had done before? Well, I guess it's good I didn't post this yet, because I hadn't totally figured it out, but this is what I was thinking. So I thought that this actually worked in all the cases, because it looked good here and it looked good here. But if I look at the stuff that's above 0, well, if I take 1 and I subtract, a is above 0, if I subtract 1/2, then, no, then I'll get what I'm supposed to. Oh, I think I realized what it is now. I think I understand. Okay. Alright, so here's my new hypothesis. Now you're watching me actually figure, because I thought I had this, and I wrote down a formula that I thought was the formula, but now I'm reconsidering. okay, so this is 1/2, but this is 1 minus 1/2, and the reason why I think that's interesting is because this is whatever 0 gets sent to minus f tilde of a, which is the thing that covers 0. So I can get the correct coefficients if I do this, and what I want to point out is that for this one and this one, this is f tilde of the thing that I was looking at minus f tilde of its immediate cover, the thing that's right above it. Now for this one, it doesn't have anything that's right above it, so it might make sense that that's just whatever the value was. So that's okay. So this is my hypothesis, is that if I say that okay, so I think what I'm thinking now is that f is actually equal to f tilde of 1 plus the sum over all x's that are not 1 of f tilde of x, let's see, f tilde of x minus f tilde of x. I guess I'll do x hat. I'll say x hat. X hat is the x hat is the cover of x, the thing that's right above it. No, I can't say that because, okay, I see. Maybe it's all of its immediate covers. I think we're gonna have to do a bigger. I'm gonna not hypothesize about what exactly the formula is because I need to do more experiments. But I'm convinced, based on this, that the quantity that I wrote down, that this f tilde thing is the correct thing to intuitively think about the translation. And the reason why I feel like that is because, I mean, this looks quite natural. The issue is that A isn't the only immediate cover of 0. It's actually one of 2, right? Because I'll just draw the picture again. I've gone too far. So here we have 1. Both B and A actually cover 0. So, okay, so 0, so f tilde assigns to 0 the quantity 1. So we're putting a 1 here, we're putting a 1/2 here, we're putting a 1/3 here, and then we're putting a 1/3 here. And so, so the idea seems to be that, so for what A actually gets in the convex combination, we just end up doing this minus this, and then for B we ended up, or sorry, for 1 we just had this, and then for 0 it looks like we had this. Oh, sorry, I was writing down what f tilde was. So actually this wasn't 1/3, this was 0. Okay, and then for 0 we had this minus this, but if we had subtracted off the other cover of it too, it would have been fine. Although, how do I want to say this? I guess as I had reasoned before, there's only going to be a single chain worth of things that have distinct values assigned to them. Yeah, so I basically had previously reasoned last time that whenever you did this process of figuring out what this function f tilde was, it's only going to assign non-zero values to things that are in some kind of increasing chain like this. It's impossible for it to do anything else, and it's always going to give 1 to 0. Yeah, so I suppose I could say something like immediate cover in the chain that is corresponding to this f, but that feels like a little bit less natural maybe. So I think what I want to say is something like take maybe this f hat of x to be maybe f tilde of x minus the sum over all say y. This is like y covers x. It's like a curlier one. So all immediate covers of x do f tilde of y, and that agrees with the formula that I have so far. And it's just basically only one of those immediate covers will actually have a non-zero quantity assigned to it, but I can just write down a nice formula by saying subtract them all. And then I don't have to actually like put into the formula like which one it is. It'll just work. Okay, so now the question is, will this still work if I do it on a different example? Okay, because if I can do this, then so the idea, so my guess then is that f, well, I don't need to write f of x, but that f is equal to the sum over all x's in the lattice of f hat of x phi x. So that's what I'm thinking. This is my current conjecture. Yeah. So well, just let me know if you have any questions, but otherwise I'm going to just start testing this. So yeah, so this actually wasn't needed for the original this wasn't needed for the original argument that was in the paper I wrote in grad school. It's a more general thing, but I was so curious about it and I started messing around with it, and I was like, I've got to put this in. And that's how I end up taking years and years to post papers, and they end up becoming like 50 pages long, because you know, it's just hard to like, I don't know. I just want to, it feels like so close. It's only a few more hours of work. I'll just add it in, and then like, you know, and then time passes. So anyway, okay, so let's try this. Let's try this on a different lattice and see what happens. And so the lattice I want to try it on, to see if I actually get something that makes sense here, is so this lattice, which is known as N5. This is the pentagon. And so it's very similar to what we had before, but instead of just A and B, I'll have A and then B and C, and then 1 is up here. This is still a lattice. And if we do this geometric realization thing, what we're expecting is that, so there are two maximal chains, and one of them is the left-hand one that should give us a triangle, 2D triangle. And the other one is a chain of length 4, which should give us a 3D simplex. And so this is going to be like, a 3D pyramid that just touches this thing over here. So if this actually works in general, then we would expect that it would work on this, and it should give us this thing. Okay. So, well, I guess let's try to take some convex combination of things that I expect to be in here. So let's say that we have some function from this lattice now, which is, you know, it's now N5. I'll just keep writing, you know, L instead. So let's say that I took I don't know. Let's say that I took 1/6, 0, and then I took 2/6. Well, okay. Instead of writing 0L, I should write phi 0L, so I remember what it is I'm doing. 2/6 phi b, and I don't know. Let's see. I have 3 so far, so I need another 3. Okay, so I'll say maybe 1/6 phi c, and then 2/6 phi 1. Okay, so now this will give me this. Okay, so these coefficients add up to 1, so this will give me a convex combination that's sitting inside of this, somewhere inside of this tetrahedron here. That's the idea. And so so if I do this, let's see, I'm gonna get 1/6, and then okay, I'll choose a total order again and identify f with f0L, f of A, f of B, f of C, f. Okay, and so this would be this. This would be, okay, so for B I would just have 0 and B. For C, I'm going to have 0, B, and C. And then for 1, I'm going to have everything. And so this is going to be giving me, well, just 1 in the first coordinate like always, and then what shows up in the second coordinate, just 2/6, and then what shows up in the third coordinate, 2/6, 1/6, and another 2/6, so that's 5/6. And what shows up in the fourth coordinate, we got a 1/6, 2/6, and nothing else, so that's 3/6. And then what shows up in the last coordinate, just 2/6. Okay, I'll not reduce the fractions because, why bother, right? Okay, and now we have to compute f tilde of each of the elements. So f tilde of 0, well, what's the biggest thing we can put in and just have everything above it be the downset, the principal ideal for 0? It's just 1. What's the biggest thing that we can choose where if we look at all the numbers that are at least that big, we get the principal ideal associated with A? Well, let's see. If I put in 2/6, it'll include A. I can't put anything in bigger and still get A. But if I put in 2/6, then I'll also then I'll certainly also get 5/6 and 3/6, so I get everything. So by my slippery definition there, using the join of an empty set of things, I know that that's actually 0. And then if I do this to B, well, remember B was this coordinate, so I have to put in 5/6 to get B, and then I'll just get the downset for B. So that's okay. So that's the biggest thing that I can put in. That will give me the downset for B, and then if I do C, I will get that. Well, I have 3/6. I have to put in 3/6 to get to 3/6 is the biggest thing I can put in and get C. And if I put in 3/6, then I will certainly also get 2/6. No, I'm looking at things bigger. Okay, let me double check. So 0 always gets 1. A, if I put in 2, 6 so that I get A, I can't choose anything bigger than 2, 6, so I wouldn't get A. Then I would also have to be getting 1, which would mean I'd have to get everything. For B, if I put in anything bigger than 5, 6, it wouldn't work. So 5, 6 is probably the biggest thing I could put in that I would get B. And then if I did that, then I would only get 5, 6, and 1, or 5, 6, and 0, which is the principal downset for B. Okay. So now for C, if I put in anything bigger than 3, 6, then I wouldn't get C. So I have to put in 3, 6 is the biggest thing I could put in to get C. And if I do that, well, what's bigger than 3, 6? 5, 6, and 1. And so that would be the 0 of the lattice and B. Okay, this makes sense. So then this would be 3, 6. Okay. And then finally for 1, well, I have to put in 2, 6 in order to get the 1 of the lattice. But if I look at stuff that's greater than or equal to 2, 6, well, that's everything. So that is that principal downset. That's the biggest thing I can choose. Okay. So I have all of these guys. So now, what I'm going to do is, so I believe that, okay, so now I'm going to write down what these f hats are and hope that this is actually the correct formula still in this lattice. So if I do f hat of 0, I'm going to have f tilde of 0. Let's see, if I do f hat of 0, I'm going to have f tilde of 0, and then, well, okay, I'll write it down. I'll just copy the formula. That's the great thing about this, right? I can just copy and paste stuff. So what was my proposed formula? It was this. Okay, so this was the proposed formula, and so then if we do this, then let's see, f hat of 0, so it's going to be f tilde of 0 minus f tilde of all the things that are immediately covering it. So it's going to be f tilde of 0 minus f tilde of A minus f tilde of B. So that's going to be 1 minus 0 minus 5, 6, 1/6. And what was the coefficient of 0? It was 1/6. And then I'm feeling good. I'm feeling like I know what I'm doing, which made I wrote down that formula with the supremum, and I was like, this is the this is obviously got to be the quantity associated to the individual elements, right? It's the biggest thing where you get that downset. Like that's why it was the definition of the other way of thinking about this, right? That's gotta be what contains all the information. Anyway, I'm still feeling good about this. Okay, so now let's do A. So that means I should do f tilde of A minus f tilde of all of the things that immediately cover it, which is 1. But here I have a problem, right? Because, here I have a problem because before what happened was that, so if I did this to B, oh, actually it would have been wrong. I see, I understand now. So it actually would have been wrong if I did it to B too. So it has to be defined to be this if, it has to be defined to be this if f tilde of x is not 0, but if f tilde of x is 0, then I don't want to just subtract off these covers. I think I'm just gonna have to. I think I'm just gonna have to do it by cases. Yeah. Unfortunately, I think that I'm gonna have to say it's this if, I mean, there's ways of adding something to the formula that cheaply to make this happen, but it's gonna be this if f tilde of x is not equal to 0, and otherwise we're just gonna define this to be 0. So, I mean, I think that's fair. All right. So then by my cheap definition, then this is just 0 because f tilde of a was 0. All right. I don't care about that one. And then f tilde of b. So, or f hat of b, it'll be f tilde of b minus its f tilde of its immediate covers, which is actually just c. And so, okay, so then, well, what did I get for b? It was 5/6 minus 3/6. Okay, 2/6. Yeah, I did it. Okay, I'm like totally convinced that this is the correct formula. Okay. So I think I've pretty completely convinced myself that this is the right formula, and it works just for whatever lattice. Finite lattice. Yeah, there should be an infinite modification of this as well, but I'm pretty convinced that that I can translate between these now. Okay, cool. So well, anyway, the reason that I care about this is because then what I was thinking was that we should be able to define meets and joins in terms of the convex combinations, right? That was like the original goal. And so so for instance, in this one, so say that I had say that I had this convex combination. Well, actually, maybe just let me write down the formula in general. It's not, I don't know if it's going to make it any more clear to give a long example. So then the idea is that if you have something that looks like the sum over all x's of some convex combination, so ux, phi x, and you want to do the meet with the sum over all, well, I guess to make it less confusing, sum over all y of vy phi y, then okay, so then what I'm thinking is that if I do things in these no. Okay, if I do things like the like obvious thing in these coordinates, right? Then I will just be doing what I said at the beginning didn't make sense. I can't just take like I can't just multiply the coefficients, right? That's not going to work. So what I want to do instead is I want to take this presentation and I want to take a presentation like this, and I want to use it to actually compute what the meets and joins will be in terms of these coefficients. That was the goal. So okay, so if I have two different functions from my lattice to 0, 1 that actually belong to that geometric realization, so they are, in other words, they satisfy that condition. Well, so what does that mean? We know that for each s fs, which is all of the things in the lattice with the property that f of x is greater than or equal to s, and gs, which is the set of all x's, so that g of x is greater than or equal to s. These are always some principal Okay, so that's what we know. So because we're inheriting the order relation from just saying that, like, you know, functions are ordered, are one's function's less than or equal to another one when it's like pointwise less than or equal to, our natural guess for f meet g from L to 0, 1 would be that f meet g of x would be the minimum of f of x and g of x, and then similarly for the join, but it would be max instead. And so let's see, if I do f meet g according to that definition, S, then this would be the set of all x's where, well, this definition of f meet g of x is greater than or equal to S. And this would be all the x's with the property that, that what? The minimum of f of x and g of x is greater than or equal to S. Okay, and so, well, what does that mean? That means that certainly this contains all of the x's in L, so that f of x is greater than or equal to f of x is greater than or equal to S, and it's also going to contain all of the x's, so that g of x is greater than or equal to S. So certainly it has to actually contain f, so fs, so fs union gs, right? Because if I have an x that satisfies this, then yeah, it has to be that. Okay, but it's possible that, let me see about this, but that means that, okay, it's possible that the union of those two things could not be a principal downset, and this is what was bothering me before. Like, I want to say that this is it may actually be in one of the papers that already exists, and I'm just trying to refigure this out without looking anything up, just because I want to do it for the exercise. So I want to say that it's the pointwise minimum of the two functions. That's what's most natural, given that we're inheriting the ordering that's like the pointwise partial ordering. Like this is the natural thing to do. But if it's going to make sense, then I have to be able to actually show that this thing, at the very least, satisfies this property, but then I would actually have to show that it's also the greatest lower bound for these two guys. And so, okay, well, no, maybe it's not the, okay, let me actually think more carefully about this. If I have an x that satisfies this property, that means that either f of x is greater than or equal to g of x, which is greater than or equal to S, or the other way around, like g of x is greater than or equal to f of x is greater than or equal to S. Either way, I see. Because for some x's, it might be the case that for some x's, it might be the case that f of x is greater than g of x, but for other x's, it might be the case that this is actually bothering me now. Let's see, because yeah, it depends on each individual x, so I'm not sure that I can actually. Well, okay, so if there's an x that satisfies this, certainly it must be in fx, or in fs, because f of x is greater than or equal to s. Oh, it also must be in G. I understand now. So what is it? What does this contain actually? It doesn't contain the union. So if x is in here, right? What does it mean for x to be in here? It means that whichever one is smaller, we know that f of x is greater than or equal to s, and we also know that g of x is greater than or equal to s. It's just saying that whichever is the smaller of these two, it's still greater than or equal to s. So we actually know that this contains not the union, but the intersection of these two things. That's what I got tripped up on before. Okay, so we know that it has to contain the intersection of these two things. Oh, but on the other hand, if I had something that was in the intersection, then regardless of whether f or g was bigger, it would have to be here. Okay, so I think that this is equal. I think that's what I'm thinking. I think that that's actually equal to the intersection. I'm sorry, what? You didn't really mishear me, though.
Did you say equal or equal?
No, I said equal. I'm not talking about category theory right now, so I don't have any reason to talk about equal. I should tell you about evil sometime. How many people in the chat know what evil is in a technical sense? Are we as categorical as we were last time? Do we have people who know about evil? I'm not talking trash about category theory, by the way. It's a real thing that people talk about. Okay, so anyway, I believe that I've convinced myself that that's the intersection, and so okay, so if that's the case, then certainly this claimed meat is actually in there, but I need to make sure that it's actually the greatest lower bound. But okay, I think I'm pretty convinced for now. I think that this is what it is. So then I'm going to go with this, and I'm going to say that also then I would define f join g as being defined as the maximum of f of x and g of x. But now the thing is that this doesn't come from an explicit description of these guys. I want the description that's in terms of the original elements of the lattice, so that is using this translation. So if I know that f is equal to the sum over all x's of these f hat things times these phi of x's, and I know that g is equal to the sum over all x's of g hat of x, theta x. Maybe I'll use y's. Then f meet g of, I guess I'll say z, is going to be, well, it's going to be the minimum of f of z, g of z, which is going to be the minimum of, okay, so f of z is then the sum over all x's, f hat x, phi x, z, and then g of z is going to be the sum over all y's, f hat y, phi y z. Okay. And so, okay, so let's see. So then if I want to I want to say this. Okay, so my goal is to have a formula for, no, I think this is the opposite direction from what I wanted. So my goal is to have a formula just in terms of the convex combinations. In other words, okay, let me write down what I actually want to solve for instead of just blindly plugging things in. So what I want is I want to be able to say, I don't know how to really choose an arbitrary f and g that satisfy that condition without, like, you know, just going through and making all those choices. I want something that's parameterized as though it's, you know, in terms of the convex combinations. So then what I want to say is, if you give me the sum over x of, well, of these guys, right? Let's imagine that we know how to convert back and we know what our original f is. If you give me this, and you also give me g, I want to know how to choose the components so that this is the sum over w's of I don't know, alpha w phi w. So I want to be able to choose those alphas in that convex combination. So that's my goal. So so that means that I know how to compute the mean if I do it in terms of taking the minimum, assuming that that is in fact the correct thing to do. Okay, so I guess I do have to try to compute this minimum, and then I'm going to, okay, so if I can do that, then I can use that information to help me to find what these are. Okay. Well, let's see. So if I would like to figure out, okay, so if I'd like to figure out what this quantity is, right? Sum over all x, hat of x, phi x, z. Well, remember, this was the indicator function of the principal ideal associated to x, which means that this is just going to kill all terms that are not given by z less than or equal to x. So in other words, this is the same thing as the sum over all z less than or equal to x of just f hat x. And for identical reasons, we'll have, if the sum, we do the sum over y of g hat of x, phi y of z. This is the sum over all z is less than or equal to y of g hat of y. Okay, so that would be what I see. Okay. So that quantity is f meet g of z. Okay, so that is f meet g of z. Okay. But now these alpha w's, another name that I could give to that would be f meet g. I don't have enough room. Let me give myself enough space here. So another name I could give to that would be, I want to sum over all w of f meet g hat of w is phi w. So I want that. I want those coefficients. So I know that this is expressible as the minimum of sum over all z less than or equal to x, f hat x, and then the sum over all z less than or equal to y, g hat of y, okay. And if it's the case that these aren't just zero, then there will be some interesting collapsing that happens, right? Because it telescopes like where did I have my formula here? So remember, I chose these things so that it was like the element minus f tilde of that element minus f tilde of all the covers, and so like then if you take everything less than or equal to x and you keep adding these things together, you're going to be yeah, you're going to end up canceling a bunch of stuff out. Well, well, yeah, I guess that's just basically, yeah. Anyway, anyway, I don't want to think any harder about what that's going to actually turn out to be, but okay, so we have some formula for this. I think I'm just thinking about the fact that it undoes what I just did before, but let me not dwell on that. Because my goal is to be able to write in terms of these, right? I'm imagining that I have the f hat of x first, so that I have the convex combination first, and then I'm going to go back and then I'm going to go back and I'm going to use that in order to get a formula for the other thing. Okay, so I know how to write that, and so now my goal is to actually have this. Okay, so if I want to know this instead, then what is this going to be? Well, okay, it's going to be that tilde of z minus sum over all, I don't know, gamma, which cover z of f meet g tilde gamma. So since I can write that in terms of the convex coordinates, I need to be able to write the tildes in terms of the convex coordinates. Okay, I see. So the tilde thing for z would be the largest value of, it's like the largest value of s that I can choose, so that I will get the principal downset associated with z. Okay, I should write this out. So f meet g tilde of z is going to be okay, so it's going to be the supermum over all s 0 1 with the property that if I do f meet g s, I get exactly the principal downset associated with z. Okay. Alright, yeah. So I need to actually be able to compute that quantity. Okay, so let's see. In order to compute that quantity, I'm going to have to figure out. Okay, so when is F meet G S that principal downside? So F meet G S is going to be all of the x's with the property that F meet G of x is greater than or equal to s. So it's going to be. Oh wait, didn't I already think through this? Yeah, it's Fs intersect Gs. Okay. So assuming that reasoning was good, then it's still just as good down here. And so let's see. Okay, so if that's what that is, so that looks like that should still be Fs intersect Gs. And let's see. So if I have that that's Fs intersect Gs, then, well, I want that the intersection of those two is this principal downset. Okay, but how can that happen? If Fs, so say Fs is some principal downset generated by, I don't know, U. And Gs is some principal downset generated by V, principal ideal for V. Saying that the intersection, so if Fs intersect Gs is equal to this, well, then that would mean that these ideals intersect at Z. Okay, but how can that happen? Well, so certainly okay, so certainly if I take these two ideals and intersect them, then that has to contain the principal ideal. That has to contain the principal ideal generated by U meet V. That's definitely true, because our picture would be like, here's the stuff that's below U, here's the stuff that's below V. Somewhere down here is U meet V. So we definitely have that all the stuff that's below U meet V is in there. And so, on the other hand, if I had something, okay, so that direction is easy. If I have something that's below U and it's below V, it's definitely in the intersection of these. On the other hand, if I look at the intersection of these, if I have something, okay, or maybe I'll say it this way, what would it look like if I had something that was, no, I don't want to do the contrapositive. But on the other hand, if I had something that was below U and it was also below V, then it would have to be less than or equal to U meet V, because U meet V is the greatest lower bound. So if I have a lower bound for both U and V, then I actually have something that's below the greatest lower bound. So actually this intersection of prime ideals is actually just that. Okay. So Okay, so then because of that, I now know that F meet GS, well, I know that that is actually the same thing as, well, whatever ideals these corresponded to, it's the intersection of those corresponding elements. Okay. So, okay, but I'm not really sure how to say that then. Let's see. So I'm trying to find the biggest S with the property that if I take the prime ideals corresponding to Fs and Gs, that the meet of those generators for those prime ideals is Z. So the biggest thing I can choose so that occurs. So I guess understanding that, at least the way I've done it, understanding that is the obstruction to writing down an explicit formula in terms of the convex combinations, like in general, and not just like, you know, you can do it for specific ones, but like I want something that's not ad hoc. I want like a general formula. But okay, so this would be the biggest choice of S, where if I take the prime ideals for Fs and Gs and I intersect them, I get this prime ideal, the one determined by Z. Well, let's see. I'm uncertain if I can write down a formula for doing this in general. I think I should actually try to work out a specific case, like in coordinates, like using this technique but in coordinates, and then see, or like in a specific case I should do this with the convex coordinates and see if I can figure out what this is supposed to be, because this is feeling like something that is going to be difficult to describe. Let me try drawing a picture. That always helps. Okay, so here's my lattice. Okay, so Fs corresponds to some principal downset. And let's say it's this. So this is like Fs. Maybe GS corresponds to a different principal downset, which is like this. This is like GS. And so, I mean, their intersection is going to be some other principal downset that is determined by this. And the question is, what is the largest value of S for which? What is the largest value of S basically for which the intersection of those guys is the principal downset for Z? Well, let's think about it. So if this is what we got for these choices of S, bigger choice of S. Yeah, this might be a little messy to try to do without working through an example. Does anyone have any questions or comments or anything? I think that was a good half hour of me just going through this. Yeah, I definitely wasn't going to write this up in a couple hours and post it on the archive. I should just post the original thing. That I have probably. Oh, maybe I will. We'll see how this week goes. I'll either do the rest of this and then post this along with it, or I'll just say I'll just give the coordinates for the one that I actually did explicitly. Because I have a result that's not just this, that I actually proved when I was in grad school, and so I'm really tempted to think about how to do this in general in terms of the convex coefficients instead. Hey, buddy. Do you want to say hi, Dobby? Oh, what is this? Oh my God, are you wearing a little necklace?
He's a little fairy.
He's a little fairy, huh? Okay. Debbie, do you want to say hi to your 4,000 admiring fans, buddy? Yeah? Are you ready? Yeah. Okay. He didn't really get up here, but that's okay. Okay. He huffed. All right. Yeah, so let's see. I want to be able to figure out what this quantity is. And so, well, certainly, okay, I need this Fs to contain the prime ideal generated by Z, and I need that to be true for GS too. But there can't be anything bigger than Z, which is in both of these. Yeah, I can't think of a nice formula for how to write that value of S right now. Is this just going to be unpleasant? I don't know. I mean, okay, so it's like I can get the actual I can get this quantity here, and then this will give me that function that corresponds to F meet G. And so I'm trying to think if there's another way I can go about this now. So, like, the reason that I couldn't just take the vector that I had for like F before, right? Like, a natural thing to ask is you know, like once I have this, right? I'm given some function F that does this, right? Why can't I just directly read off of this what the coefficients of these things should be, right? Because this is saying that, you know, I mean, it's a convex combination, but like it's a linear combination of these vectors, right? The problem is that there's a different vector which I didn't use in this combination. I used with coefficient 0, right, which is phi a. And so phi a, did I write down what it was here? Well, right, phi a would be 1, 1, 0, 0, 0. So like it's conceivable that I could choose perhaps a different a different combination of things and get this. Let me think about this. Is it? Oh well, no. If I have one of these for each of these principal ideals, then if I had a combination of them that was 0. No, I guess it is a basis, right? I feel okay. Now I'm feeling like this should be a basis. Okay, because what do these look like? So let's see. So, for instance, for this guy, we have that. So this is going to be this. Okay, doing A, B, C, and then 1. Okay, I was thinking something would end up being redundant, but that's not true. And so, oh, that's not 0. Okay. So I guess I can, okay, so I guess I can just, okay, so I guess there is a change of basis that will take the convex combinations. Yeah, because this is a basis, but it's not the standard one. So there's a change of basis that will take me to like the convex combinations or vice versa. So okay, so that means that what? Yeah, and I'm convinced that I'm now convinced that this works in general, because if I just choose any linear order that's increasing, if I choose any linear ordering that is compatible with the ordering in the original lattice, then I will have 1s on the diagonal and all 0s above it, and then whatever down below. Okay. So there's a change of basis that takes me from the standard one to the convex, to the one that I want to use for my convex combinations. And so okay, so okay, so then I guess what I want to say is okay, let T be this change of basis. So T of the indicator function of x is defined to be the indicator function of the downset, which is what I called phi x before. Okay, so that's a perfectly good change of basis. And so the thing is that I know in the original basis I know how to compute f meet g, because I know that this looks like it's supposed to just be this. Okay, but what I want is I want to be given something that's in the convex combination basis and compute the mean. And so, well, I need okay, so then what I need to do is I need to say, okay, I have yeah, I guess it's just kind of amounts to the same problem, where I'm given something that looks like a sum of ux phi of x's, and I'm given a sum of vy phi y's, and then I want to compute the mean of these two things. And so, I mean, yeah, I guess this is the thing. So it's a straightforward calculation to add up all of these vectors and then take the minimum on each of the components. But the thing that is not as clear is if I want to add up, I want to then rewrite this as wy, or not wy, let's see, alpha w phi w. So what I get when I do this in like the obvious way of like adding up some scalings of the individual indicator vectors is that I get something that I'm thinking of in terms of the original basis, but I want something that's in terms of this, and so if I plug z into the left-hand side, right, I'm getting sum over all x less than or equal to z less than or equal to x. So it's the indicator for the principal downset for x. So I'm adding up all overall z less than or equal to x, ux, and then I'm adding up, okay, and so then I want to take the minimum of that and also sum over all y of, no, not all y, sum over all wait a minute. I'm picking up a ux for each, no, for each x greater than or equal to z, I guess is what I want to say. Yeah, for each x greater than or equal to z. Okay, and then similarly, I'm picking up a vy for each y greater than or equal to z. Okay. And then I'm taking the minimum of those, and that's what that value would be. So like when you say the minimum side, do you mean like, so why it is that I'm, wait, let me go back. Okay, so my thinking, and I didn't go back to check because I wanted to just refigure it out again. My thinking was that if you have these two functions from your lattice to the closed interval 0, 1, which satisfy that condition on the level sets, then their meet, because the ordering that I know works as a lattice ordering is the one that's inherited from just the pointwise ordering for functions from L to 0 to 1. And so it seems that it should be the minimum should be the minimum pointwise should be the meet. And so in order to check that this actually makes sense, certainly these level sets should satisfy the desired property. And so then I was looking at this and I was seeing that it looks like this level set is exactly the intersection between these two things. And so this also has to be a prime ideal, and so it satisfies the condition. And so then I said, yeah, this I'm not going to argue this anymore, but this seems like this should be the meet of f and g. Is that what your question was, or did you have a different question? So I'm trying to, oh, okay. So now I'm trying to figure out how can I express the minimum in terms of these convex combinations in a way that's like intuitive. So like I can do it, like I can do it in like any specific concrete case, but I want like a general formula or method that makes sense in terms of like the lattice itself for computing meets and joins when I'm using the convex combinations. But the other way that I was thinking of translating it like made me have to compute something that I don't know how to compute right now. So like again, a thing that I can compute in a specific case, but I want a nice general formula. And so, well, okay, so this minimum of these two things should be this should be f meet. Okay, if my f and g are those things, there should be f meet g of z, or yeah, f meet g of z. Okay. Okay, so like in that sense, I have a formula for how to compute the meet for what f meet g of z is for each z, if I'm given the convex coefficients. So I guess the thing is now I want to compute I'm not sure what make video specifically means, but I just leave everything in. Like, unless something absolutely acrimonious happens that should be cut out of the YouTube video, I just leave it in. And so, for instance, if there was like an unreasonable amount of spam or something, I might cut it out. But like, you know, otherwise, I just leave it as it is. Yeah. So you can go watch the previous 36 hours of this on YouTube if you'd like. You can do a marathon and, you know, make a drinking game of it or whatever you'd like. You know, have a snack every time I drop a minus sign or something. I don't know. But so like I know how to compute this. I know how to compute. Yeah, it's just something to, you know, it's something to study to or whatever. You can watch me go for a while and check back in and see how it's going. So I know how to compute this meat in terms of the convex coefficients. But now the thing is that I want to actually know, you know, I want to be able to express the convex coefficients for the meat. And so I guess the thing is that, you know, if I have, you know, so I know that if I have, well, okay, let me write it this way then. F meet G is equal to the sum over Z. Well, what are these quantities that I know how to compute? They're the coefficients in this basis, which is like the standard basis. So in other words, I know that this is F meet G of Z times 1Z, and so that's the coefficient in the standard basis. But I want to actually write that as a sum over some W of some alpha W VW, and well, that means that what I guess I should be saying is, well, so that means that I have sum over Z of F meet G of Z times, well, what is 1Z? It would be that change of basis, T inverse, applied to phi Z, and I want that to be equal to maybe that's not a profitable way to think about this. So I know that I want that equation to hold. And so if I apply T to both sides, if I apply T to both sides, I'm going to turn this into a phi Z, but I'm going to turn this into something else. On the other hand, if I apply T inverse, then I'll turn this into a 1W, and I'll turn this into something else. Okay, but let's try that. Okay, so that means that if I apply T inverse to both sides, then if I apply t inverse to both sides, then these are just constants that I know how to compute what they are. And so this is the sum over z of that f meet g z that I computed before. And then t, whatever t inverse of 1 z is. And that should be equal to the sum over w's of alpha w t inverse of phi w. But I do know what that is. So this is the sum over w's of alpha w 1 w. And so if my goal is to compute alpha w, then if I take the dot product of both sides with 1w, or with one, like, okay, if I have a specific coordinate that I want to know, I guess is what I mean. So, okay, so I'll take the dot product of both sides with one, I don't know, sigma, I guess. There's one sigma, sigma's in the lattice. Okay, so one sigma dotted with the sum f meet g c t inverse 1z is equal to sigma dot sum over w alpha w is equal to alpha sigma. Okay, so that's a formula. So in other words, okay, so that means that my, in other words, my alpha w is going to be like 1w dot oh, well, I should actually write out what the formula is. So the minimum z less than, or, no, which one is this? Yeah, z less than or equal to x. Ux z less than or equal to y dy, and then times t inverse of 1z okay, so these things are just some constants that are associated to each z. Yeah, so it seems like, I guess at the end of the day, it seems like, I think the reason that people don't want to write down the formula, at least as I've seen so far, I haven't seen anywhere where it's explicitly written down, is because I need to use this change of basis. I need to use this change of basis in order to accomplish this. So I mean, it is a formula, and think this looks good, but it's unfortunate because, well, I mean, okay, it's not that bad, I guess. I guess what this is saying is actually that, I guess what this is actually saying is that, if I think about this, right, this is the coefficient, this is saying that the coefficient of the mean is exactly this coefficient of this thing. But then if I think about what that's saying that, yeah, okay, it's like, okay, it's saying that the entries in this, in the standard basis, are the coefficients for the mean. Ah, I see. So yeah, it's like just saying, like, if you compute this formula in the standard basis, you'll get a vector. The entries in that vector are the coefficients of the indicator functions of the principal ideals that will give you the corresponding convex combinations. Yeah. I mean, okay, it kind of makes sense when you think about it, though, in that, like, there's no way that I was really going to be able to use the, like, somehow all of the entries from each of the possible phi sub x's were going to have to interact with each other somehow, right? Because in terms of the standard basis, they're indicator functions for ideals, so they have lots of entries that are not zero. So you would expect that they would all interact with each other, and so this seems to be the way. All right, now let's test this by seeing if I can actually write down the formula just for the 4-element Boolean algebra that I looked at before. So if this is going to make sense, then I'm going to have to say, okay, here's 0, A, B, there's 0, A, B, and 1. Okay, so I'm going to say that my standard basis is just going to be the indicator function for 0. I apologize for the nested subscripts. Indicator function for A, indicator function for B, indicator function for 1, the lattice. Okay, and then my ideal basis, I guess I'll say. My ideal basis will be phi 0, phi A, phi B, and phi A, phi B, and phi 1. Okay, so with respect to these matrices, the change of basis that I want, right, I'll call this T. So T sends 1, 0, L to, right, which direction did I define this T? I want to be consistent with what I said before. It sends 1x to phi x. Okay. Okay. So now this is still this is still like the standard basis over here, because this is a change of basis from the same. Okay, I guess to be clear, I'm going to write the matrix with respect to the standard basis, like in both sides, right? So what does 1, 0, L get sent to? In other words, what does 1, 0, 0, 0 get sent to? It gets sent to the indicator function for the corresponding principal downset, which is just that. So this is like 1, 0, L, 1A, 1B, 1, 1, L. Okay. And then similarly for what does 1A get sent to? It's sent to 1, 1, 0, 0. 1B gets sent to 1, 0, 1, 0. And then 1, 1, L gets sent to just all ones. Okay. So I need to compute T inverse, which I will just have the computer do. I mean, I'm sure it shouldn't take too long to do by hand, but I'm just gonna. Why put forth the effort? It's late in the day for me. Just make sure I won't make a mistake or anything anyway. I always forget to put the outside braces. It has to be a list of lists. It's not smart enough otherwise to know. Okay. So I have the inverse matrix. All right. so that's going to be 1, negative 1, negative 1, 1, 0, 1, 0, negative 1, 0, 0, 1, negative 1, and 0, 0, 0, 1. Okay. All right. Okay, so now my formula told me that what I'm going to have to do in order to find the coefficients for the meat is I'm going to have to apply the inverse matrix to each of the individual basis elements for the standard basis. So that's going to give me 1, 0, 0, 0. This is going to give me, oh, sorry, that wasn't 1A, that was 1, 0L. This is going to give me 1A, is going to give me minus 1, 1, 0, 0. 1B is going to give me minus 1, 0, 1, 0, and minus 1, or T inverse of 1, 1L is going to give me 1, minus 1, minus 1, 1. Okay, so then the claim would be that if I take sum for x of ux phi x, and I want to take the meat with the sum over y of vy phi y, then I should actually get the sum over, let's see, how this is, sum over w 1w dot sum over z of the minimum sum over z less than or equal to x ux sum of z less than or equal to y vy, and then t inverse of 1z. Okay, and so now we can do this explicitly because we have enough information to do this explicitly in this case. And so, in other words, if I have, I'll just call it u0 phi 0 plus ua phi a plus ub phi b plus u1 phi 1, and I want to take the meat of that with v naught phi naught plus va phi a plus vb phi b plus v1 phi 1, then I am going to get some stuff. Okay, so I forgot a coefficient. So it's that quantity times phi. Okay, times phi w. That was the other thing. Oh, there's not enough room. Okay, I'm not really sure what you're saying there, but if you elaborate, then I may be able to give you some feedback on that. But yeah, I was missing a phi. Phi w over here. I'm just gonna do a little arrow. I ran myself out of room. This is the coefficient of phi w. Okay. Oh, okay. Nice. So, all right. So, well, I know what all of those things are supposed to be. And so I guess the next thing that I would need to compute is, okay, maybe I'll leave that for now. What's the next thing I need to compute? I'm going to compute the minimum. Okay, so what's the minimum of, well, if we do 0, if we do, okay, I'll just go through case by case. So if we do z equals 0, then what are we going to get? Well, the minimum of 0 less than or equal to x over u of x, so sum 0 less than or equal to x, u x, sum over 0 less than or equal to y of vy, and then t inverse of this 1 sub 0 is what? 1, 0, 0, 0. Okay. I see, but there's no more information that I can give than that at this moment, because there are various possibilities for what these values are, and so let's see, if z was a, then, well, I'd have a similar thing. I mean, I guess I could just say, okay, if 0 is less than or equal to x, that's everything. So I suppose I can just drop that completely. But I still don't know what those sums are in general. I don't have any more to say about that. And so, well, if a is less than or equal to x, I mean, I'm just basically saying I'm summing over a and 1, right? Because those are the only things that have that condition. So I'm going to here have just ua plus u1, and then va plus v1, and then whatever the t inverse of 1a would be, which would be minus 1, 1, 0, 0. Okay. All right, so I'm going to end up getting all of these and then adding them together. Okay, so I did 0 and a, and I actually think I can probably do the rest of them and then check it out. So, okay, so like for instance, when we compute the coefficient of phi 0, it's going to be 1 times this quantity minus 1 times this quantity. I see. Yep, so we can definitely give an explicit calculation for it, but it's like you're going to have to add up various subsets of the coefficients, and then yeah, you're going to have to add up various subsets of the coefficients, compute the minimum for each of them, and then take a linear combination of them. I see. Oh, it's so much weird. Yeah, it is so much weirder in convex coordinates than just taking the minimum. The convex coordinates are so natural. It seems like it's so much more natural to do it that way. You really feel like you can see where you're at on the lattice. Yes, I'm a professor at the University of Colorado Boulder. That's correct. So yeah, I don't know if anyone's ever called me an academician. It certainly sounds like an English word. It's just not one that I think I've ever heard used. I'm curious about the etymology of it. Do we speak different dialects? Is it something that's more common in another part of the world, maybe? I don't know. Maybe I should start calling myself an academician. Not sure. Oh, it's the auto typing. Okay. Well, okay, great. So I can be the first academician. It sounds like I'm on a mission. It's all good. Okay, So maybe I'll do the rest of this calculation, but at this point I feel like I'm convinced that there's not a much simpler formula in this case, and that this is the reason why people don't present it this way, is because it's painful to do it this way. Okay, so then if I do b instead, well, I'm going to add up all the coefficients that correspond to what? It's going to be the principal upset corresponding to b, right? These were summing over the principal filter, in other words, the principal filter corresponding to 0, principal filter corresponding to 0, except actually that shouldn't have been the sum over x, it should have been the sum over y. So these are the principal filters. Okay, you know what, I'm starting to take it back. I feel like this has a kind of, is a nice thing to it. There's like a kind of duality. Because here it's saying like I should sum over the filters, the principal filters for 0, the principal filters for A, the principal filters for B, and so it's like the dual to the ideal. So this would be UB plus U1, VB plus V1, and then whatever the thing is for B, so minus 1, 0, 1, 0, minus 1, 0, 1. Yes, thank you. Yeah, I appreciate it. I'm glad that you're getting something out of it, even though we might have different backgrounds. I'm glad that it's, there's some amount that is accessible. It's nice. Yeah. So let's see. So that's for z equals b, z equals 1. Well, okay. The principal filter for 1 is the easiest one. So we just have u1 and v1. And then for this one, what did we have? We had 1 minus 1 minus 1 1. Okay. So 1 minus 1 minus 1 1. All right, and so now we can figure out our coefficients. So for 0, so what is the coefficient? Okay, so coefficient of P naught, what's it going to be? It's going to be the minimum over, it's not going to simplify any though, because we have these minimums everywhere. So we're going to subtract the minimum, I see, we're going to subtract the minimum over these filters. And then we're going to subtract the minimum over these filters. And then finally we're going to, so there's like some kind of inclusion-exclusion, I think, happening for this, which is nice. Okay, I'm starting to feel better about this. I'm starting to feel like this is like quite natural, actually. So it's like, yeah, it's like saying you take the minimum over these principal filters, but you subtract the minimum over the next level of principal filters, then you add in the next level of principal filters. Now, it could be just because this example is really small, but I'm curious. I'm curious what is going to happen if I. So I should think. What is this change of basis? It's like saying you have the principal ideal that corresponds to this thing, and it's like saying each time you go down a level, you put a minus sign, and then you negate again when you go down another level. But it could just be, let me think about this. Okay, I think I'm not going to be able to be certain in the next 10 minutes, but I'm starting to feel like this change of basis is actually this. No, it can't be this. It can't be this inclusion exclusion thing, because if I can do it to the lattice n5, then that wouldn't make sense, because I can't like. No, because I could still say. No, because if I assigned -1 here and -1 here, I'd want to put 1 on B, but then I'd have contradictory information about what to do with 0. So the next step would be, what happens when I do it to this one? Maybe let me compute the inverse of maybe let me compute the inverse of the matrix for this one really quick. So let's see, it would be 5 1s, and then 0 1 0 0 1. Sure. Okay, so the way that I did this one was, well, okay, I'll just write it down. All right, so I'm convinced that I can see what's going on, but now I'm wondering what's going to happen with a lattice that is not graded. It doesn't have the grading like that. So what happens when I have something like this instead? Well, okay, so 0 is going to get sent to 0 1, or not 0 1, 0 A B C 1, 0 A B C 1, 0 B C 1 A. Okay, so A gets sent to this, B gets sent to, no, not 0. C gets sent to this, and 1 gets sent to this. Okay, so if I, let's see, okay, so then I have all 1s, and then 0 1 0 0 1, and then 0 0, and then 3 1s, and then 4 zeros and 1. Okay. Oh, I skipped a level. Zero 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 1 1. See, that's my inverse. Okay, so my inverse matrix here is going to be 1 minus 1 minus 1 0 1 0 1 0 0 minus 1 0 0 1 minus 1 0, and then 0 0 0 1 minus 1, and then all zeros, and then 1. Okay, so what is this saying? If I look at 0, it's just getting sent to the thing that has a 1 there and zeros everywhere else. If I look at A, it's getting sent to something which has a 1 at A and then a minus 1 at 0. If I look at B, then it's like the thing that has a 1 at B, a minus 1 at 0. Nothing weird to us so far. If I look at C, what is it doing? It's giving me something that has a 1 at C and a minus 1 at B, and then nothing is 0 at 0. Okay. And then if I look at 1, what am I getting here? I'm getting a 1 here, and then I'm getting minus 1s at A and C, and then nothing at B, and then a 1 here. So I feel like I don't have a great deal of intuition about why that's the case, like philosophically, like what this represents in terms of the structure of the lattice. But it's definitely not as simple as straight up inclusion, exclusion. What about the C part? So this was C. C got a 1, and then B got a -1, and then everything else got zeros. That was what happened at the one that was for C, and then for the top one, we got -1s at C and A. So we got 1, -1, -1, 0, and then we got a 1 down here. So that doesn't look quite like inclusion exclusion, because it's not alternating between -1s and 1s, which wouldn't really make sense anyway, because if we took 2 different paths, we get 2 different answers. So this looks like it's a little bit different from that, and so I'm not really sure what the intuition is here. I can definitely write down these formulas in all cases. Of course, it still remains to prove that this is actually correct. Like, one should, I should verify that this is actually giving me the right answer carefully, but maybe I'll save that for something else. I don't know. But I think that's about it for today. I really appreciate all the great questions and all the interest. Like, it's really it's always fun. It's always surprising. I never quite know what's going to come up. I definitely would like to talk about polyhedral products at some point, so I appreciate the suggestion. As I mentioned, Fred Cohen was definitely a mentor to me, and it'll definitely be very nice for me to talk about polyhedral products again. Oh yeah, thank you. Yeah, thanks for joining the live stream. Yes, nice to meet you as well. All right, well, I think in that case I'm going to call it here. Thanks everyone for another great evening of Math Research Live. I'll catch you next time, and thanks for a great lucky number 13 too. All right, see ya.